So, firstly, I wanted to draw a relation between this nonlinear optics and the response theory that we use for this theoretical calculation of spectra, but couldn't really do that. But I'll be mainly discussing the fluctuation-dissipation theorem today. So, this fluctuation-dissipation theorem actually was there. The idea of this theorem was there from the very beginning, like from the very beginning of 1900s and all. But this theorem was actually given by Ryogo Kubo. He was a Japanese physicist, and he mainly worked in non-equilibrium stat mech and condensed matter physics. So let's start with from where does this idea of this fluctuation dissipation comes. So firstly, we all know about Brownian particles, right? Like suppose if we have a container and there is a liquid inside that, then, and if we tag a particular molecule in there, then suppose there's a container and there are liquid molecules in there, and suppose we're tagging a particular molecule, then we know that the motion of this molecule is going to get influenced by its surrounding molecules. So the effect of the surrounding molecules on the particle of our interest is actually given by two forces. One that we call the systematic part of the force. Sorry for the handwriting. Another is random part. So suppose we are applying some external field in our system, then our normal observation will be that the particles will get arranged here. And we'll get a response because of the external force that we have applied in our system. Now, this external disturbance that we are giving from outside and the internal
Rimpi,
fluctuation of this, yeah.
if the particles are neutral particles, then how the external electric field and
Yeah,
rearrange the particle
sorry.
orientation?
Yeah. Considering the Brownian particle is a charged system, charged particles. Yeah. So, yeah, as I was discussing, so if you're applying this external disturbance in the system, then in presence of this external disturbance, there is going to be a response. And in absence of this external disturbance, there is going to be some internal fluctuations in the system. So the main idea of this fluctuation dissipation theorem is getting a relationship between this internal fluctuations and the external response. So this basic, not basic, but this idea can actually be philosophically connected to our own lives. Like whenever, like if we say like we are in a, whenever we are in working, like we were in school or colleges, we were having some fixed time schedule that we had to go to our classes at time and do things. But if we think about it in adult life and there is no restrictions in us, then that discipline is somehow lost. So irrespective of that discipline, we know that we are working, right? So it's like kind of our internal fluctuations, and in absence of this discipline can also lead us to the destination where we want. to go. So in the year 1905, Einstein gave this diffusion constant equation of a particle, where he said that diffusion of any molecule is related to kBT by m gamma. So we know this kBT is the thermal energy of a molecule in equilibrium, and this m gamma is our frictional constant. So like so suppose suppose there was a tube or a somehow vessel where no, there was a tube where liquid molecules were flowing. Now I've applied a potential in this part of this tube where this potential is not equals to 0, and now this, in presence of this potential, these liquid molecules are going to drift. So it's going to have some drift velocity. So that drift velocity UD is given by this change in potential gradient by this frictional change in potential gradient by frictional constant m gamma. So we know that diffusion processes are generally observed when there is a non-uniform case, obviously, right? There has to be some gradient to move for molecules to diffuse from one part to another. Now, this non-uniform diffusion process, Einstein assumed that diffusion processes is a not, sorry. Einstein assumed that diffusion processes are definitely going to happen in non-uniform solution. So from that assumption, gave a relation that at infinite time, things are going to get at thermal equilibrium, and the diffusion coefficient will be given by this following expression that I wrote right now. Now, we know that position of a particle at xt minus x0 can be given as its velocity over time. Now, if we put this expression in the above diffusion equation, then we can say now this can further be simplified into now, if you remember from the very first expression here, we can write m gamma is equals to d by kbt, and just putting the value of this d here. So this is our mu, which is not the dipole moment but the mobility, which is the inverse of frictional constant, and it is related to the fluctuation of velocity of the Brownian motion. And this whole relation mu is equals to this velocity correlation of this Brownian motion particle that undergoes this Brownian motion was manifested by Einstein in the year 1905, and hence we know that the idea of the fluctuation dissipation theorem was there from the very beginning, and it actually came into action when we consider the Langevin classical equation of Langevin and the random force. So the most simplest example of a free Brownian particle, the Langevin equation of a free Brownian particle, given by now here you can see this is our frictional part that we discussed from also the Einstein's ideology of Brownian particle or Brownian motion, and this part is our random force. So this term is due to the random collision of the surrounding molecules that is having some effect on our Brownian particle. Now, for simplicity basically, there were two conditions that were assumed that this RT is Gaussian and the correlation time is very short, like so it's like when our particle is having a large number of collisions, its relaxation time of the molecule, it's definitely going to be very, very much larger than this correlation time. So basically, this is the second assumption. Now, from this equation, trip one, the diffusion constant is given as by m square So here we can see that the random force, like the previous expression where the mobility was given by the velocity correlation, here the diffusion coefficient is given by the autocorrelation of this random force. Now after this, just a second. Now there is another assumption that this Brownian motion is taking place in thermal equilibrium. So this diffusion constant can now be given as gamma by m to kVt. So since it's in equilibrium, they are going to be equal, the frictional constant and this thermal equilibrium energy. So from the previous expressions, we can write m gamma equals to and then putting the value of this du here. Now we can consider just like when I showed you that streamline motion of the liquid particles and yeah, here in this tube, where we at a certain position we considered the potential was not equals to 0. So similarly here, if we consider the Brownian motion in a potential field, then start is equals to u is our velocity. Then the Langevin equation given by this. Here the potential gradient expression is just added in this general Langevin equation. Now, the nature of this random force is independent of the presence of any force field. So we all have, like, not we all, but generally the people who do this molecular dynamics simulation, we are aware that the power spectrum or the density of states is given by this Fourier transform or this or velocity autocorrelation function. So the power spectrum for any stationary process can generally be given as now consider y as any physical observable. It can be velocity. Now, it's taking Fourier transform. It, and they have the correlation.
Rimpi,
Yeah.
why do you call it power spectrum? Like velocity autocorrelation function?
Because it tells us about the density of states, right?
Density of states.
Like, like which states are populated.
Which states? So from velocity autocorrelation
Hmm.
function, how do we get the information about density of states?
Origin of power spectrum, sorry, is not related to velocity. This is general term. Means this actually nomenclature is given due to the first time when this Fourier transformation is calculated. This is from the current correlation
Yeah.
to get the power response. So from there, I think this name, this nomenclature remains same, the power spectrum, and we use it in different different
Like
yeah.
or any linear response like structure in the like क्या बोलते हैं उसको, in the current setup, like LR, which scheme that was, I forget it. Yeah, in the current setup, so they actually computed the power response function. So from there they get this type of expression. Yeah, I actually the connection. Yeah, and my second doubt is how is it different from the dipole autocorrelation function?
Like, that's a different physical observable, right?
Yeah.
Like, what is different?
Like velocity autocorrelation function Fourier transform, we just call it power spectrum. And we also said to get the accurate dynamical information from spectroscopy, we should compute dipole autocorrelation function. So why this is so?
Okay.
Like what type of information is missing from the velocity autocorrelation?
Rimpi, this is general, na? Y omega. Y you are for general observable. Y t means
Any physical
you
observer, like
any
it can be
physical
mu t
observable.
here. Huh.
Yeah.
Yes. Mhm.
Velocity and dipole autocorrelation are exactly means if we write the dipole in terms of coordinate and charge, write it down.
So basically, if we approximate our dipole function as a linear function, then will it be accurate or not?
Yeah, if we means
We just write
if
mu
we
is equals to
write
q
down,
into r.
Yeah. So that's
yeah.
the real dipole. No, sorry, linear dipole function.
Huh.
Right. So if
Yeah.
you write down this form, then I think the velocity autocorrelation and dipole autocorrelation will be exact, right?
Yes.
Mhm.
It will be exactly means connected with that
Yeah,
charge.
it connected. Yeah, it
To
will be
the
connected.
charge. Yeah.
Yeah, but does that answer your question?
Yeah. So basically, I wanted to know that how these two functions are connected or not, or how different it is actually.
But I thought you were asking like why do we get the exact response from dipole moment and power spectrum from velocity?
No. We also compute power spectrum and dipole autocorrelation function, right? But what type of information are we are missing from the power spectrum, and what type of information we actually get from the dipole autocorrelation function? That's my concern actually. So basically, if our dipole function is linear, if we approximate our dipole function as a linear function, then we get similar type of information from both power spectrum and dipole autocorrelation function. But if our dipole function is nonlinear in nature, I think then the spectra will be different or information will be different.
Means if we cannot simply write down it as q into like ab initio water,
Yes.
we approximate it by linear function, but means in general there is no simple charge multiplied by position of oxygen like that. So there this expression, there these similarities does not be easily visualized, that dipole and velocity. But for force field, where for point charge, there you can means exactly see that dipole and velocity are similar with the charge factor. And the information means velocity, we can get to know the every motions in the system. But for dipole, we can get to know that which motions will be interacting with the electric field, with the AC field, oscillating electric field. So two informations are important, means for that sense. One give the full vibrational information, and one gives the active vibrational information.
Yes. Yeah. Okay.
So that was saying was this. Yeah, so let's just put.
And Rimpi, just one point. Actually, I was talking to someone like she was doing she is doing surface spectroscopy. Surface means solid surface, and some molecule or atom is dissociating on the surface, like H2 dissociation on some surface, silica surface or palladium surface. So they actually compute velocity autocorrelation instead of dipole autocorrelation. So I asked her why they are doing this, but she answered that what she answered that if our dipole function is q times r, so that's why I didn't quite understand that, but yeah, I don't know why they are computing velocity instead of dipole.
I think they try to say that means it is similar, means dipole
Yeah,
and
it is
velocity
similar.
with that
Similar.
approximation. But
Mhm.
when this approximation does not hold too much,
Yeah.
like if we have metal, then
Mhm.
this kind of thing would be disaster. Means mu q into r. Means more delocalized nature of the electron will be less. We could less approximate.
Yeah, but
like
he said it's on the surface of metal only, right?
Yes, on the surface of metal, like some.
So
That's
in
why
that
I
case,
think that it is not easy to get dipole information from metallic surface. Means it is still under.
Okay. Mhm.
okay. She is here, like in ITK.
No.
Okay.
She's in like Peter Salfran's group in Berlin. So
Okay.
they do actually this kind of surface spectroscopy, IR spectroscopy, for the molecule dissociating on the surface like this. For reactive system, IR spectroscopy. You can just look into that group.
Mhm.
And Rimpi,
Yep.
there if you put back means if you put that expression of yt into that expression back,
GY.
then you get the double Fourier transformation. Means g omega
Yeah.
can be calculated from y omega itself using this double Fourier. Yeah, that is
Okay.
one theorem. Means one can efficiently calculate, because Fourier transformation one can efficiently calculate using first Fourier efficiently and also very accurately. So this many people do this kind of trick to calculate this power spectrum. Or
What's the significance of doing this double Fourier transform?
no, there is no, means it is same mathematically, but numerically or
Okay.
in terms of
Less costly?
calculation, if we calculate means if we can, because it is finite, this all the correlation function will be finite. So whenever we truncate it, error comes from this truncation part. Okay. But instead of this, if we do this Fourier transformation, okay, so Fourier transformation actually most efficiently approximate the truncated part also. Okay.
Okay.
So that's why many people prefers this way, means double Fourier transformation to get this power spectrum. There is a theorem, Green-Chen theorem in spectroscopy. Spectroscopic people use.
What theorem?
Green-Chen, you see the Barbara Green-Chen paper.
Okay. Okay, I'll look into that.
There is a square of this function and then Fourier transform.
Okay. So in this expression, if I just replace the physical quantity y by our random force, be given us some gr by omega prime, and this gr is given us by So from here we can say that the power spectrum is actually determined by our friction. That means the resistance to the system actually tells us how the states are going to be populated and how is the energy going to be dissipated, the thermal energy, the microscopic thermal energy. So this thermal force, which is the R, is actually the result of thermal fluctuation. So this was actually given by Nyquist theorem in the year 1928, where he showed that random electromotive force EMF appearing across register is determined by the impedance, and impedance was actually connected to this external electric field that we have applied. Now, actually, the paper that I've chosen for this today's talk is too long, so I will be just writing the equation here because won't be able to derive so much right now. So in equilibrium, this velocity autocorrelation can be given as square e to the power minus kappa into t. Now, if we differentiate this, suddenly we're going to be minus gamma, and then write this u square as t0 plus t, like just using this expression here, or definitely t greater than 0. Now, the correlation between this velocity and any random function should be 0, provided that t1 is less than t2. So this means that d of t0 initial time, we differentiate with respect to initial time, should always, this correlation should be 0. So we say it's going to be a stationary process. However, we say this equation is actually contradicting the above equation here. So Kubo in the year 1965 and Moody in the year 1965 and Kubo in the year 1966 individually gave a natural extension of this Langevin equation, where they said this velocity So this part is our frictional force, this is our random force, and this is our external force. So this gamma T, actually the frictional force, it represents the retarded effect of the frictional force. And we assume that the average random force is going to be 0. So initial time velocity and this random force correlation is going to be 0 for obviously t greater than t0, and it does not depend upon our external force kt. Now if we consider that this k is a periodic external force, so it will depend on k0 cos of n omega t, then this equation, this mu dot t, may be given as r of omega k0 e to the power I omega t, where this mu is our mobility and given as so from now this so this is the fundamental expression of our fluctuation dissipation theorem. Which was given by Kuo and obviously Mori as well, and it was later extended to linear response theorem, correlation and correlation spectra, which are actually the proof of this fluctuation dissipation theorem, which today I don't think I will be able to discuss. Maybe some other day. But the main thing here is how fluctuations actually in non-equilibrium system as well, the fluctuations in equilibrium system can be related to the external force in the non-equilibrium system. That's the whole idea of this fluctuation dissipation theorem. That's what I wanted to discuss today. So, if anyone wants to ask something?
U average T equal to R means random.
No, not, that's different.
real.
That's the response. Like, yeah, it's something not the random force that I was using for that.
Okay. R is
Yeah.
used for real also. This is what is R here? And
Here I don't think it like it's like the equation gives the response it was written, so I think it's the R response.
I mean, if we expand this expression,
Hmm.
then how could we write it? Means
Like
if
you
we
want to say.
unfold, if you unfold these R, means R is some short version. Understand? But if you unfold this thing, then how do you write?
I think it is the real part because the complex admittance is given by this. Yeah, you're right. It stands for real.
Okay.
Yeah.
Then UT average equal to mu omega. I am thinking means this expression from where means the derivation. Go to the
Okay, so this
Yeah,
one
just
came
one
from-
point. Okay.
Hmm.
So here your noise is not delta correlated, right?
because we assume now because external force.
Yeah, that's why I'm asking. So your noise is not delta correlated here, right?
Yeah.
Yeah. Okay.
Yeah.
So
So
if we assume our noise as our usual delta correlated noise, then we'll get our so-called known fluctuation dissipation theorem, right? Yeah.
The classical one.
Yeah. So this is just the general form of fluctuation dissipation theorem.
Yeah, the most fundamental.
Yeah.
Then what is the noise correlation? Means RT or
That I was discussing when we didn't right. Here you were discussing it, right? So at that time we didn't, I think, consider this correlation between the velocity and this random force, which created a contradiction between this expression and this expression, where one was saying that it should be a stationary process, so there should not be any correlation, it should be zero. But due to the presence of friction, where did it go? Yeah, it cannot be zero for any time greater than t greater than 0. So sorry, what was the question again? Like where did the random force correlation go? Was that the question?
RT0 plus T means it is delta function in the simplest assumption. But in that specific case, what would be the expression?
Okay. I don't know actually. One second. I don't know actually. Sorry.
Actually, like for your stationary delta correlated noise and for Markovian process, so the fluctuation dissipation theorem you get, what is the expression like?
That is R of if you take your physical observable as R, then it's going to be R T0, R T0 plus T, and then 2 pi G of R delta function of that T1 minus T2.
Yeah. So basically, it will be like KBT equal to M gamma something, right? So that is for Markovian process, stationary and delta correlated noise. Right?
That is for Markovian, but stationary is this one, no?
Yeah, that was also for stationary process. Yeah. So
okay, here, that one is for stationary Markovian and
delta correlated noise.
Okay.
Yeah. And now here, what's the difference? Like, is it Markovian or is it it is Markovian also, right? Yeah, because gamma is constant here, or gamma is constant, no?
Yeah.
So
No,
that
it was
means
not
this is
connected.
Markovian.
Hmm.
And your noise correlation is also delta correlated here or not?
So in the previous one, like where I gave this R of omega and where there was one assumption that we took now that this tau of R is going to be greater than where it this assumption was there. So this assumption is not valid in the case here. That's the difference here. But how is it making?
Okay. Just scroll down.
Hmm.
Scroll down. Yeah, scroll down. So, okay, so basically mu omega is the mobility, right? Like,
Mobility. Hmm.
so mobility is related to the velocity correlation Fourier transform. U is velocity.
U is velocity.
No, that's the doubt. No? In the previous expression, like in the mu omega expression. So mu omega, you have written mu omega equal to 1 upon m times 1 divided by I omega plus gamma as a function of omega, right?
Function of omega.
But this is true only when gamma is non-Markovian, right? Gamma is some time dependent, right? History dependent gamma. If gamma is our constant, like for Markovian process, then it is just a constant, right?
But like
Yeah.
from the paper from where I have been discussing this, they have written that like for the where I said that this assumption is no longer valid here, so they have written for the generalization of Brownian motion theory to random motion of the particle, which is not necessarily heavier than the particles interacting with it. So this means that the time scale of the molecular motion is no longer very much shorter than the motion of the particle under observation. So that tower that does not get valid.
Yeah,
so so in order to meet this requirement, we have at the same time to abandon the assumption of constant friction override and to introduce generally a frequency dependent friction.
Yeah, that's why.
Gamma omega.
So that's basically it is a non-Markovian process. Or it is derived from generalized Langemann equation, right? Yeah, that's why I'm asking. Yeah, that's okay.
It is non-Markovian. It is also written in the expression of Langemann equation.
Yeah, it is from generalized Langemann equation. Derived.
Yeah, but where did this random correlation go?
Random correlation, I think there is no specific, this is the only assumption you made here, means our average for random part.
Yes, it should be 0. Yeah, this
average random is 0. Okay.
Yeah.
And this correlation with random
velocity is also
later
0.
time, yeah, this is 0.
Yeah.
These two are the only assumptions.
These two are the assumptions.
Only assumptions. Okay.
And the that Gaussian property assumption remains.
Okay, random will be Gaussian, but not delta function.
No, it's not mentioned. Yes.
Means I am thinking if delta function, whether this delta function and these Markovian things are connected or not. is because you already made the friction non-Markovian, means history dependent.
Mm.
So friction to be history dependent, the random noise means can't be
Zero.
delta function, because friction and this random part is connected by fluctuation dissipation theorem. Okay. So one is history dependent, other is not. That is not possible. So I think this is the reason that's why this R is not delta function here, is Gaussian, and mean is 0. Yeah. Okay.
Okay.
And this mu omega, mu omega is the power spectrum part of this velocity. Okay, this is a Lagrangian shape. Okay, not Gaussian shape. Okay. Okay, means there is a homogeneous broadening in mu omega. Means this homogeneous broadening comes from this history-dependent friction. Okay.
Yes.
This broadening, this line width is actually history-dependent friction. So yeah, this will explain the means broadening part. Means otherwise it is earlier it will be delta spike.
That's not
In the actual case, yeah, means when these particles, suppose water, if we tag a water molecule, means, in a water bath, then we get a broadening. Means it would be history dependent. Okay.
Okay.
You can share the paper also.
Yeah, I will. I'll share it in the group.
Yeah, and so basically this mobility is connected to the susceptibility. So
Yeah, and and
Yes,
the correlation
yes.
spectra part, they will talk about this dissipative part and softive part. Yeah, I
mobility
couldn't
is
discuss that.
mobility is related to the position velocity autocorrelation function or susceptibility, basically in the chi of x.
Chi of, yeah.
And this is not the fluctuation distribution theorem. Like you have
Like this is
written,
the fundamental expression, right?
Fluctuation distribution theorem is like relationship between fluctuation, that means noise, and
internal
dissipation, that means
fluctuations.
frequency. Friction. Okay, so relationship between the friction and the noise term is the fluctuation distribution theorem. So this is, you can call it, this is mobility or dynamic mobility or susceptibility, you can call it. But the general expression for fluctuation distribution theorem from non-Markovian process or generalized Langevin equation is different, and which is like is a relationship between the gamma as a function of omega, which is friction, and it is related to the noise part, which is in your expression r of p0 and
random force.
Yeah.
Okay. This is what I wrote from this paper. It was written in there that this is a fundamental expression.
Yeah, you can derive it from here also, but yeah.
Okay. So I'm
Yeah, basically I was a little bit wrong because this is called the first order fluctuation distribution theorem, like first fluctuation distribution theorem.
Yeah.
And the main fluctuation distribution theorem, which is the relationship between the friction and the noise term, which is called the second fluctuation distribution theorem, like this. Yeah.
And that for second fluctuation dissipation theorem, you also need to consider this equipartition law.
Sorry?
Like for this second fluctuation dissipation theorem, where you said this frictional part and this random force part is connected, you also need to assume equipartition law of energy. Right? Yeah, that's it. That is okay. Right? Just put mu of u square equals to kVT. Okay. So happy Sunday, everyone. Bye.
Okay, so if